have a person as a height of the object is 1.7 meters tall, stands 0.74 from a reflecting globe in a garden. So the globe will look like this. This is the globe. And the person is standing right there. The distance from the object to that globe is 0.74 meters. If the diameter of the globe is 18 centimeters, the diameter, so the distance from end to end here is 18 centimeters or 0.18 meters. Where is the image of the person relative to the surface of the globe? So what's the distance of the image? And I don't have to graph this, but if you want to graph it, what you have is a convex mirror, not concave, because you're looking at the shiny side on the outside. That's what you're looking at. It's a globe, so you can't see the inside. So you're basically looking at something like this. You're looking at like this. Now notice diameter is 0.18. The radius is going to be what? Isn't that half of that? 0.09. Somebody singing out there? So it's the focal point, which is half of that. What is half of 0.09? Is it 0.045? So if you want to graph it, there's your object right here. Now this is a diverging lens. I'm sorry, this is a mirror, not a lens. Convex mirror. So the first one, the P line, the parallel. Oh God, please don't sing. And they're going to deflect or reflect, not deflect, reflect is like coming from the focal point. Go in that direction. The P ray, the F ray going through the focal point, so it's pointing in that direction, and is going to reflect parallel to the axis. This is the F ray. And where are the three going to meet? Well, actually, there's two of them here. There's the P ray, the F ray, and what was the third one? What did we call it? I threw my paper away. I had it sitting here. We call the P ray, the F ray, M ray. That's for lenses, I think, the M ray. The middle lenses. Center, yep, the C ray. And we call this C ray, and that's going through the center. That's where the center is. And where's the deflection of that? It's going in, it's going to deflect or reflect going back. And that's where the image is going to be, right here. Because if you extend this line, well, I'm a little bit off here. Yep, actually I'm okay. If you extend this line here, deflection, if you extend it, that's where the image is. We don't have to graph it for this. It's nice to know where the image is. Notice the image on the opposite side. It's upside down. It's normal. It's not inverted, I mean. It's, what do we call it? Like inverted and normal? We had a name for it last time. What was the name we used?
Real?
Well, it's this is a virtual image on the opposite side. But beside that, when it's not flipped, we call it not inverted, but do we have a name for it? I think erect is the name that we use. I don't know if I use that or not. I just say not inverted. And what else we know? It's reduced, right? The question is, where is that image? Now, if I use graph paper, I probably could measure that distance and see where that image is if I use a scale, but I'm not going to do it that way. It's nice to see the picture. I want to do it mathematically. So here we go. 1 over I plus 1 over O equals 1 over F. This is a convex mirror. We're looking for the I. We know where the object is. 1 over what? 0.74 equals 1 over F. What is F equal to?
0.045.
Almost. Tyler. Almost had it. He's at 0.045. I said almost. What's wrong with that? How about a negative? Convex mirror.
Yep.
Convex, the focal point is negative. What is it? R over 2. Negative. So you do the math. This will be a negative number. Turn it on. I get some crazy number. Let me try it again. 1 divided by negative 0.045 minus 1 divided by 0.74. Yeah, negative. I got a negative now. Negative 23.6 roughly. What is I equal to? 1 over negative 23.6. Which is negative 0.042, or is that 4.2 centimeters inside that thing. The image is going to show up there. Inside. It's going to look like it's sitting inside that. So 4.2 centimeters, 2 significant digits. Yep. And the next question is how big that image? We know it's shrunk there. How big is it? So let's go to the magnification. The magnification, it's negative I over O. Negative, that's a negative, negative becomes positive 0.042 over the object, which is what? 0.74. I'm using meters here. Which is 0.057. Two significant digits, yep. 0.057. That's the magnifications. 0.057. Submit. Let's try it again. 0.042 divided by 0.74.
In centimeters.
Oh, in centimeters. I'm sorry, in centimeters? No, magnification has no units. Oh, the height of the image. Oh, the height of it, that's the magnification. So the height of the image is going to be 0.057 times the height of the object. Why? Because magnification is the height of the image over the height of the object, which means the height of the image is equal to the magnification times the height of the object. I thought they want the magnification. They don't want that. So we know the magnification is 0.057. How high was the object? How tall the person was? 1.7. And that's roughly 0.096 meters, which is what? 9.6 centimeters tall. That image is going to be 9.6 centimeters. They're not asking for the magnification, they're asking for the height of the image. 9.6 centimeter tall. Correct. And it's not inverted. So notice it shrunk. That was the whole thing, yeah. The fact is plus, this is a plus here. It tells me not inverted. The fact the image is negative here, negative tells me it's virtual image. So when the sign for the image is negative, it's virtual. When it's positive, it's real. The magnification, when the sign is negative, is inverted. When the sign is positive, not inverted. So that's 34. Let's look at number 36. We have a telescope. It uses a concave, here we go, concave mirror. Not convex, concave mirror. That means the mirror is like this. This is that black side of the mirror, the shiny side on the inside. That's a concave mirror. Has a diameter, this comes from a sphere that has a diameter equals, wow, 2 inches. I thought it was meters. 200 inches. That means the radius is what? The radius is 100 inches. And the focal point is positive the radius over 2. So my focal point here is 50 inches. Is there another scope here? Or there's 2 lenses in it maybe? A Halley telescope, the 200-inch diameter concave mirror, the Halley telescope on Mount Pelor has a focal length. It says the focal length is not that, actually. The focal length or could be that 50 inches. Is that 16.9 meters? Is that what the 50 inches? Let's see if it is actually. What is 50 inches equal to? Convert that. Inches, meter. 1 meter has how many inches approximately? One meter? 36, so that's not it's not 16.9 meter. So I don't know, they said it has this focal length, so maybe there's two lenses, one in the front, one in the back, I don't know what's going on. But let's say it says has a focal length. So I want to use their focal length of 16.9. Okay, I'll use that. An astronaut stands, that's the distance of the object, stands 21.6 meters in front of this mirror. What is the image, or where is the image located? Her image. So we have a concave. Quickly here, picture-wise. This is the focal point. This is the astronaut, 21 inches after that. So the top one goes like this. Deflect, that's parallel, it's supposed to be parallel here, it doesn't look like parallel. Comes through this one. The other one goes to the focal point. That's the F. Comes up parallel. Bless you. So it looks like her image. I can do the third one, but that's where the image is. You can see it's upside down. It's hard to tell the size because I'm not really graphing it to scale if it's bigger or smaller, but inverted. We'll have the math tell us where the image is. One over I plus 1 over O equals 1 over F. I is unknown. O is 1 over 21.6. F is 1 over 16.9. This whole thing here looks like has no use in the problem. All the information there. Why they gave us what the diameter is and all the stuff, I'm not sure yet. Unless there's two lenses and I'm missing the whole story there. But for solving it, they're giving us what the focal point and the object, and they're looking for the image. One divided by 16.9 minus 1 divided by 21.6. 0.0128, I think. 29. And what is I? 1 divided by that number. 77.7 centimeters. Or meters. All these in meters. .7. That's where the image is going to be. Correct. So that was the correct answer. So this was useless, really. Just to make a nice story. You know? Now the image, we see where the image is. Is the image in front or behind the mirror? This side is considered the front, that's behind. You can tell from the image, from the pictures in front. You can also tell from this. Why? Because this sign is positive. If it's positive, that tells you it's real image. Real means in front. Same side as the object, in front of it. So the image is in front and is that a real image? We said yep, real image. Positive image, that's real. Submit. What is the magnification? Now the magnification is negative I over O. Negative 77.7 divided by O, which is 16.9. That's a negative 4. How many significant digit? 4.60. The negative tells me the image is inverted. and this tells me it's larger. Got bigger, 4.6 times bigger. So the magnification of the image, I don't know if they want the minus sign. I'll put the minus with it, 4.60. Minus I over O. 3 significant digits. 4.596, I mean 5, I get 4.60. Give up. It says 3.60. Am I blind? 77. Negative I, 77.7. We get that answer correct. Divided by 16.9. Am I seeing things correctly? 4.597, right? So I got 4.60. 4 they go in 3.6. Magnification of her image. Oh. She stood, I'm sorry, the image, no, my mistake. Where was she standing? I used the focal point here. See the distance of the object? Where was it? It's minus I over, I just used the wrong number here. I is 77.7. The object is not 16.9. I used the wrong number. That's the focal point. The object is what? 21.6. $21.6. Need to get off this medication stuff. 77.7 divided by 21.6, 3.60. Yep. The equation is correct. Just used the wrong number. For some reason, my eyes went to the focal point instead of the distance of the object. The equation is correct. The distance of the image over the object, but the object was not a 19 or 16.9, it was a 21.6. So that's 36. $73. The next question you had is number 73. An object, 2F here. Convex lens. So this is number 73. Let's use a scale here. I don't know, roughly I can see a scale. God, I can't see the numbers on this. If I can get one that has numbers I can see. Okay, we'll put, we have a convex, this is C, this is F. The object actually was twice the distance, twice F. So this is what convex. The object was right here, twice that distance. And it doesn't tell us what numbers. It says F, this is 2F. excuse me. So the first one's the parallel one, the P ray. Deflect coming out of the F point here. And then next one is going through C, and that reflects back in the same direction. So it's going in, it's coming up. This is C. And the next one, the last one, is going through the F. Again, when deflects, this is parallel. And if I extend that line, this is what, the F ray? Where the three of them meet, which is right here, that's where my image is going to be. So I can tell you a few things about the image. Is virtual, not inverted, and reduced. So what I know, distance of the object is 2f. The focal point is negative, has to be a negative f. We're looking where the image is. One over I plus 1 over O equals 1 over f. O is 1 over 2f equals negative 1 over f. Negative 1 over f minus 1 over 2f. You got to find the LCD, which is 2f here. One over I is going to be negative 3 over 2f, and to get I, we flip that. I is going to be negative 2/3 f. Notice is inside f, 2/3 of the way, and it shows about 2/3 of the way. If you take that distance, cut it in 3, 1, 2, 3, that's where it landed. 2/3 of that distance. Express your answer in terms of f. So 2/3 f. So let me click on fraction. Do we have a fraction here? The hell a fraction? How do we make a fraction? I don't know where the fraction, so I'll make it negative 2f divided by 3. Maybe that will make that a fraction for me. Oh, it does. Express the answer in terms of f. Convex mirror, right? Oh, it's not a mirror. This was a lens question. Ah, my mistake. Redo. This is for convex mirror. Let's see what happened. That's not what the question. The question was convex lens. That's a different story. So number 73. Sometimes it's helpful if you read the question, and I am guilty. That's, by the way, a converging lens. Convex is converging lens. Let's use a scale roughly here. I'll put the lens right here. F, twice F, twice F. So this is my lens. So we draw a line from the center to the center. We treat the lens as that line there. This is the line that's going to be for the lens. So this is convex lens. This is the focal point. It's a converging lens. You put the object right here. Here we go. The first one, the P ray, parallel. And it goes through the focal point. The M ray, M is the middle. That one just keeps on going straight. That's the M ray. And the third one is the focal one. The focal one going through the focal. And it comes out parallel. Where the three of them meet, somewhere here, is my image. Notice almost actually 2F, almost twice F. This is F, that's 2F, almost. We'll do the math, probably is twice F. My image is inverted. For lenses, this is actually when it shows up on the other side, that's a real image. And size-wise, no, it looks like the same size. I can't really tell from my picture. It looks almost the same size, but we'll see. I'll do the math and see if the math agrees with me. 1 over I plus 1 over O equals 1 over F. The object is 1 over 2F. The focal point is 1 over F. Positive, because that's a convex converging lens. 1 over I equals 1 over F minus 1 over 2F. It's 2 over 2F minus 1 over 2F. 1 over 2F, and what is I equal to? 2F. The image is 2F. Is the image upright or inverted? It looks like from my picture it's inverted, right? So I can say inverted. Good. Is the image real or virtual? On the other side, that's a real image. Good. What's the magnifications? It's negative I over O. Negative I happens to be what? 2F. And O happens to be 2F negative 1. The same size. Inverted. Same size. No change in the size. Magnification is 1. So it's a lens, not a mirror there. And again, we've got to be careful where we place in it. Sometimes I don't read the whole question. This was the word lens mentioned. That's a convex lens. $85. Two more. We have 85 and 87. Okay. Number 85. An object is located to the left concave lens. Let me write concave lens. That's diverging lens. That means the focal length is negative. It says f equals 0.37. They're not saying negative. I don't know if that's negative 37 or 0.37. Does anyone know what that number negative?
Probably a negative. Looks like a negative on my screen.
Negative 37 centimeters?
Yeah, mine's just negative 30.
Okay. So it's negative 37 centimeters. I thought 0.37. But it has to be a negative because it's concave lens. That's diverging lens. Backward to mirrors. It mirrors concave mirror, that's positive f. Convex is negative here, backward. The magnification, m, equals 0.30. And it says positive here. And just take a quick look at it to see if it makes sense to be positive. Diverging lens looks something like this. And there's only one scenario for that. If this is F here, C, doesn't matter where you put the object. The parallel one is going to look like it's coming out of this one. The 1 through M doesn't bend. That's where my image is. I don't even have to draw the third line. That's where my image is. Notice on the same side, that's a virtual image. Reduced, and the math says it is reduced. It's a third of the side, or 0.3, and it's not inverted. So my picture seems to agree with that statement. The magnification is positive. Magnification is 0.30, which equals negative I over O. The question is, to decrease the magnification to M2, should the object be moved closer to the lens or farther away? That's the first question. Closer? If I move it far away, let's see what happens. Let's put a different object. Extend this. I'll use a color I'm not using on this. I'll put this object here. Same height. That'll be the first one. That'll be fine. And now the M ray, can you see that? That's where the image is going to be, right here. So if I move it farther, the image moves backward. That means I have to move it closer to that for the image to show up. So probably closer. And my math says, nope, you drew this one wrong. We can do the math and see actually what happens. Oh, you want the magnification to shrink? Yeah, notice it shrunk. So if you want to shrink, you wanted the image to be moved which way? Backward. Look at the magnification. Isn't that smaller than that one? So I got to move it backward for the magnification to shrink. Now, calculate the distance through which the object should be moved. Well, let's figure out first where the object was, then we'll figure out for the second part. Initially, 1 over I plus 1 over O equals 1 over F. By the way, from this equation, negative I equals 0.30 times O, or I equals negative 0.30 times O. So negative, or 1 over negative 0.30 times O plus 1 over O equals 1 over F. And F was 1 over negative 37. Do the math here. That's 1 over 1 minus 1 over 0.3. I'm leaving O on the bottom. That's negative 2.33 over O equals negative 1 over 37. The negative can cancel each other out. O equals 37 times 2.33. The object should be placed at 86 centimeters. Now for the second part, let's see what happens. You want the magnification is no longer 0.3. I want it to be, I think, if I remember, 0.23. Let me take a peek back. 0.23. That means that's equal negative I over O, or I equals negative 0.23 times O. And let's see where that object should be placed now to make the magnification 0.23. One over negative 0.23 O plus 1 over O equals 1 over negative 37. 1 divided by 1 minus 1 divided by 0.23, negative 3.35 over O equals negative 1 over 37. O should be 37 times, I'm canceling the negatives, that object should be moved to 123.9 centimeters. Calculate the distance through which the object should be moved. So you need to move the object. How far you got to move it? 123.9 minus 86.3, which is what? You got to move it 37.6 centimeters backward. If you want that image to shrink. $37.6 centimeters. Two significant digits, that's what, 38? 38 centimeters. Yep. So you have to move it back 38 centimeters. The change in distance of the object is 38 centimeters back. You move it back 38 centimeters, that image will shrink to 0.23 instead of 0.3. one more question. Then these are all the questions that you had for me today. '87. Convex lens again, not mirror, that's a lens. That's converging, convex lens, yep. That's converging lens. So before I do anything, it looks something like this. That's a convex lens, converging lens. Here's what we know. We know the insect was right here. So the object was 1.7 centimeters from the lens, and the magnification appears to be twice the size, 2. We're looking for the focal length. Our focal length. That's what we're looking for. If the magnification equals to 2, that's negative I over O. So 2 equals negative I, negative 1.7 over O. 2 times O equals negative 1.7. O equals, that's 2 times, you know, I should say DO, so you don't get confused. What is DO? Distance of the object is negative 1.7 oh, I had them backward, right? Object is 1.7. God. I gotta stop with the medicine. Distance of the image, negative here, over distance of the object, which is 1.7. So distance of the image equals negative 2 times 1.7. Which is negative 3.4. So notice the image is negative. That means the image is going to be here, somewhere here. That's where the image is going to be. On the same side. It is negative. That means virtual. Virtual for lenses on the same side as the object. And the magnification much bigger. So now we know what I is. 1 over I plus 1 over O equals 1 over F. 1 over negative 3.4 plus 1 over 1.7 equals 1 over F. One over F equals positive 0.294. F equals 1 over that number. .4 centimeters. So So the focal length, 3.4 centimeters. Somewhere here. The object is 1.7. So focal, that's the converging lens, that's a positive 3.4. Correct. And that was all the questions you had for me.